Markweiser in the American Scientific in 1991 said, "The most profound of technologies are those that disappear. They neatly weave themselves within the fabric of everyday life until no one sees them." Such is the topic that we're discussing today, and we have the best possible person to guide us through this topic. We'll be discussing smart systems for good. Now, let me just get to introduce the person that I have with me within the studio, and I have his book here. Dr. Nathan Amanquah is a senior lecturer in the Electrical Engineering and Computer Science Department here at Ashesi University. He serves as the dean, the acting dean for engineering and computer science. He teaches a number of electrical engineering courses, including embedded systems, IoT, digital systems design. And he has previously worked as a systems administrator and a communications engineer, as well as an automation engineer. He has 25 plus years of experience in terms of software development, and he has also worked as a consultant for a range of IT and network communication issues. His research includes applications of machine learning in embedded systems, as well as wireless technologies and protocols for IoT and wireless sensor networks. Now, if all of that got over your head, wait and get to find out the amazing knowledge that is going to come from the person I have with me in the studio today. Dr. Nathan Amanquah, welcome to this day's episode.
Thank you. Thank you very much.
Now, I said a lot of stuff in your introduction, a lot of big words. And before we get to those big words, I think it's very important for us to really get to understand the person of Nathan Amanquah. Where does Nathan Amanquah's story intersect with Ashesi University?
So I came to Ashesi after finishing my PhD in 2004. So this is my 20th year here at Ashesi. I started off teaching computer science, a lot of programming, networks, and then gradually migrated to engineering when the engineering program started. And I've been teaching engineering since 2015, mostly electrical engineering classes. So in my classes, I get students who are doing electrical or computer engineering, or those who have to do a class that I teach.
I think that's a really solid start for this particular podcast, and getting to see you have a lot of experience, especially within the domain we're about to explore. So now, quickly moving to the subject matter of the day. The first big question that everyone might have in as far as the topic we're discussing, smart systems for good. What are smart systems for good? What makes them smart and what makes them good?
Right. So this is really in reference to electronic systems and that have some computing power in them. And they might react to the environment, they might sense the environment and act on that, usually in the background without us noticing it. And that makes them smart. So we have a lot of electronic devices already, but taking them a little step further, when they begin to act on their own, usually with some machine learning or AI, they become even smarter. And we want to make them do good things for us or for society. And that's why we use the expression smart systems for good.
It's a lot of information. And I did bring my notebook just to make sure that when we're exploring this topic, we get to tackle all the areas. And I heard a lot of interesting words in there, like embedded system and like microcontrollers. So maybe this is a very good place for us to dive into your book. You have written a book. If I'm to read the title of the book, it's called Learning to Design Embedded Systems Using ARM Cortex-M0 with NXP FRDMKL 25Z. Please decrypt that for us.
Right. Okay. So the book is about, supports a class, which is embedded systems. Embedded systems are really computers that are placed into something bigger to control them. Mm-hmm. So if you think of a washing machine, it's able to control the rotation of the drum, mm-hmm. how fast it goes, how many times it spins, and tells you when the door is open or closed, or not closed properly, mm-hmm. and notifies you when it's finished washing. Right? There's a little computer chip in there that does that monitoring and control. Your microwave oven is able to time how long it should warm food for, how hot it should get, mm-hmm. notify you when it's done, and shows you the countdown as you go. There's a little microcontroller in there, a small computing device in there that does it. That small computing chip is what we call a microcontroller. So we teach students how to program these microcontrollers in order to control bigger systems. These are not your standard desktop computer. They don't have a keyboard, they don't have a mouse, they don't have a screen for you to see.
Okay.
They may not run an operating system like Windows. In fact, they won't run Windows or what people might know.
Okay.
So they might be completely bare. But getting to program these chips to do work for us in a meaningful way is what we teach. Now, that chip put inside a system, or that chip with this program is called embedded system. And it makes things act on their own usually, but we can enhance it with machine learning.
Okay. And I think you have really already started getting deep into the field, and I really do appreciate as well the way that you're breaking down these concepts to make it much more palatable for everyone who's listening to this particular podcast. And so maybe a question that someone might have is that since an embedded system, like you've said, is a computer that we've placed within a device, why do we need to place the computer within a device? And maybe do we have, for some of those electrical gadgets that we have, maybe my iron or my stove, is it also an embedded system? What makes it an embedded system? What doesn't make it an embedded system?
Okay. So I give the example of a microwave oven to begin with. If you take let's take a washing machine, the older models. Some of them are very manual. You push a button, there's a little timer, maybe with a spring, it unwinds your points and it rings a bell to tell you it's done. They are not very smart. They still get the job done, but how much better it is to have something that you push a button, it does everything, gives you an update on what it's doing, and it just makes life more pleasant, generally. Generally, people would also want to prefer something digital when there's an analog version, because it gives them some convenience, right? So once you make something digital and there's that processor in there, it makes it a little smarter than the analog one. And people enjoy using those devices. So it gives us a lot of convenience.
Okay.
But besides that, there are some benefits. For example, you can save energy better because there's some processor that can monitor what's going on around it and not use as much energy when it's not necessary.
Okay.
So besides convenience, you can save energy. It's easier to use.
Okay.
And so on. So there's a whole range of reasons why people choose something digital versus something that's analog. But not just digital, something with an embedded system.
Okay.
Because then it has additional features. There are a lot more things you can do. Let me give you a different example.
Okay.
So if you have, let's say, the police siren. I'm taking from the perspective of the person running the siren.
Yes.
He pushes the button, it comes on. It just sounds one particular kind of alarm. And until it turns it off, it stays on, right? But if you enhanced it with an embedded system, you could actually change the kind of sound it makes. You can change the frequency. You can change how frequently it's repeated. You can set how many times the alarm should sound and then go off. You could have a timer in there or a display that shows how many times it has run already.
Okay.
You can let it count down for you and things like that, which you can do with a very simple system.
Okay. So if I get what you're talking about, the traditional way that would make a siren is we have to create a circuit, some actual physical circuit. And when we get to use a microcontroller as opposed to using that actual physical circuit, it gives us more options, flexibility to create more systems essentially without having to worry about breaking down the entire thing apart.
That's correct.
Okay.
And besides in building the circuits, if you design an actual circuit to do that, you need a much more complex circuit to get it done. But with the microcontroller, you exchange the complexity of the circuits with software.
Okay.
So you write the code, it does all you want it to do. Whereas you want to design a circuit, there are many more considerations, and changing that circuit can be very hard.
Okay.
But changing the software tends to be much easier. So it's actually cheaper to design with a microcontroller than to build a full circuit.
So very closely related to this concept of microcontrollers, and like you were talking about, you can get to monitor what is happening within the microwave or what's happening within any other device that really has this computer on board. Very closely related to that is the concept of Internet of Things, and that's another domain of your specialty. What is the Internet of Things? Why should we care about it?
Right. So the Internet of Things extends embedded systems one step by connecting anything that has this microcontroller to the internet. Now you can then begin to remotely monitor what's going on with that device. You could let that device control things for you by sending a command to it. So you don't need to be present with your embedded system, but you can remotely monitor it. So if you had, using the washing machine example, you could have someone remotely monitor, or let's say a company that sells the device, can remotely monitor how it is used and tell that this device is about to break, right, based on how it's behaving. It's vibrating a lot. So you know this device is going to break. They can come to your house if you have such an arrangement with them and tell you your machine is about to break. It's time to fix it. Or they can tell it is broken and come to fix it. But for more common examples, more everyday things to do with the house, you could have your lights that are controlled by a microcontroller. You could set a time for it to come on, but you could also remotely turn things on and off. Right? So it gives you the option of remote access, remote monitoring, remote control. And this is not just for domestic things, for everything, for industry, for agriculture, for everything. Everything you can put in embedded systems that you can remotely monitor or control.
Wow. And I'm thinking about all the possible sources of efficiency from what you're talking about. You've spoken about a paradigm shift from having to do and this is something that I did read from the book, having to move from these periodic repairs to something which is more communicated by the embedded system. So getting to find out that some fault is about to happen and then they come to fix it then, as opposed to just periodically maintaining the equipment and also monitoring the energy within the entire grid and making buildings more efficient, turning off the lights when you're out of the house, turning them on when you're coming, the AC when you're coming. So I think it's something that I am really certainly excited about. And I think part of the questions that the listeners might have is how close is this experience to the African experience? Is there a place for embedded systems within our African communities? And what are some of those examples?
Right. So there's a very big opportunity, and there's a very big need for people who are experts at developing embedded systems. We have partner universities abroad. They train a large group of students, and they all end up doing embedded systems, and other companies can't get them. And so there's already a shortage of people who are skilled in this area. We have that need as well. It's true we don't manufacture as much, but even for other areas in a home, buildings, office buildings, you can always make these buildings smart and save on energy consumption.
Okay.
Right. But let's take something like agriculture. There's a large proportion of our community, of our population engaged in agriculture. It tends to be subsistence and they sell off some of it. But you could make it smarter by introducing IoT or embedded systems for that matter. You could, for example, have a greenhouse that where you monitor temperature, humidity, soil moisture, and so on, and regulate how much watering you do based on the conditions. You could also do hydroponics. In this case, you're growing plants without soil, just a nutrient fluid. You need to monitor what's actively going on with the plants and provide nutrients when it's needed. So in this area, by using electronics, you can remotely monitor the whole field and know this area is drier and therefore needs a bit more watering, but you water just enough. You're not just spraying water everywhere, as you might think in your head is necessary. But when you have electronics monitoring for you, it tells you in real time how much water you need, what's the nature of the soil, right? You can actually observe plants. Maybe plants are wilting. You can't see that with your eyes easily before it actually is too late. But using infrared imaging, for example, you could get to know that ahead of time and act. Right. So this is there. We do a lot of farming and we can make use of technology to help us.
And so I think you have really touched you've really opened up a gate to many possibilities, and my mind is running all over the place thinking about how impactful this technology could be. And you touched on a very critical point about how we have a lot of young people who have this skill and they end up being taken by multiple companies. So we actually have a shortage of them right now. And so to so many other aspiring young people who see this as inspiring, and they also wanted to become embedded systems engineers or smart systems engineers, how easy is it for them to get into this space? I know you speak about 3 strategies out of 4 within your book about like how you focus on teaching embedded systems to your students. So the question I have is, at which different levels can they get into this scope, and what are the possible career paths that could come out from learning about embedded systems?
Okay. So for someone to get into embedded systems, you have to have an interest a bit in electronics and also a bit in software development. You need the 2. So you build the electronic system, add your sensors, have your microcontroller, but you have to write code to make this work. There are many hobbies out there using different platforms, maybe Arduino or something like that. It's a good starting point. You can get something happening and make yourself happy. It's a good start point.
Yeah.
To make it really efficient, we don't program it exactly that way. We go a little lower. In the book, we have 3 different ways of doing it. One of it, there's no operating system, even as with Arduino, but you go change the registers, configure it manually using very low level bits. You go change these bits to set things on or off.
That's with assembly language.
Yes. Related to assembly.
Okay.
Right. So you can do it in C programming language, for example, and go change the bits that you need to get a device configured and behave the way you want it to.
Okay.
But sometimes you want a lot of speed.
Okay.
And efficiency. And if you want that speed, yes, if you write C code, it will be converted to assembly code for you by a compiler. But when a human being writes the code, it tends to be shorter.
Okay.
And therefore more efficient, provided you know what you're doing. Right?
Okay.
You must write good code. It will always be shorter, more efficient. So something that needs a lot of speed, needs to react very quickly. We teach how to do it in assembly, but generally we'll do it in C.
Okay.
Right? Changing bits here and there. But if you have multiple things going on, you have to kind of manage how you do it. Right?
Okay.
And so at the next higher level, we teach how to use a real-time operating system.
Okay.
Right. And so you can learn how to get all of this done in the 3 different ways. And you can get your work done. And you find that by making use of what we call interrupts, your processor doesn't have to be computing all the time or checking everything all the time. It just waits. When there's an event, it reacts to it.
Wow.
Versus what the hobbyists do, they keep checking everything to see what's happening and then react to it. You use a lot more power. It's not efficient. It's a good start, but that's not the approach we use.
Okay. And so what I've gotten from this is that you generally have like these multiple levels of abstraction, and you can get to pick the level where you decide to interact with it. Either you are really, really in the weeds doing the configuration like you were speaking about, or you're a bit higher, maybe using a low-level programming language like C, or maybe you are even much higher, like what the hobbyists do with Arduino kit, etc. So there are multiple ways to get into this field. Okay. And so now we've spoken about embedded systems. We've spoken about the microcontrollers, which are the embedded system, which are embedded within the devices. And then we have gone on to generally describe the field as it is and speak about IoT. But your research area is in something fascinating where you are trying to make smart systems even smarter. And your research area is in machine learning on embedded systems.
That's right.
So the question that we might have is like, why is that interesting, or why is that challenging?
Right. So that's challenging because we would normally use machine learning for things you cannot write a simple program for. So if you have a vehicle, a car, that you have to maintain, the reason you do maintenance is because it's expected that components in the car have a certain life expectancy based on historical evidence that on average, this is how long something lasts. But we all don't drive equally, and it's very hard to program to see variations in temperature on a daily basis, vibrations, dust, stuff. It's really almost impossible to write code. So what you do is you collect a lot of data, and there might be patterns in the data a human can see with their eyes. But with some kind of software that we call machine learning, like teaching a computer to learn from the data, you can learn the patterns and see that when these combination of things happen, then it's about to fail.
Okay.
So rather than spend money every 4 months, do maintenance, change all these things, you could actually get a microcontroller to monitor what's happening with the system, the car, whatever equipment it is, and determine when something is actually about to break.
Okay.
And change at that point. So it might be that for you, in 2 months, you need to change. For me, in 6 months, I need to change. Either way, your machine doesn't break suddenly without you knowing. And I also don't waste money changing something that's not broken.
Okay.
Right. So by learning the patterns, you can save money and be more efficient.
I think that's really something that I think is it has a lot of really good applications. And I think another question that maybe might arise. So kindly describe to our audience. So you spoke about the micro controllers, and they're these really tiny computers. And in terms of like the feasibility of it, why would it be? So we've interacted with AI. Like people have become more versed with AI, though on a very surface level, getting to learn about machine learning models, etc. But why is it hard to do that on a small computer?
So the microcontroller is fundamentally very constrained. It doesn't have power. Most likely going to run on battery. It doesn't have a lot of memory. Its processing speed is very low. This is not ideal for doing machine learning. You do machine learning on a very high-end computer. You have a lot of memory, a lot of processing power, and so on. So taking something that works in a very resource-endowed environment to something that's very constrained presents lots of challenges, and that's where the research makes it interesting. So currently, we're not doing as much machine learning on the microcontroller. We're doing a lot of inference. After the learning is done, we collect data with the microcontroller. After the learning is done on the high-end computer, we now move that information to the small controller and then do inference. It's still hard, but at least it's manageable. Okay. And that's what we're trying to do. Right? Okay. But there are advantages to doing that on a microcontroller because take a smart lock or smart doorbell that has a camera. Anytime it takes a picture of you, it must perhaps transfer that image to the cloud, do the inference there, and then send it back to that device to open the door. Right. The data must be transferred, so there's going to be some delay in getting a response. That's one. There's security implications. Somebody else can see what the picture is or what the information is. Third, even if they can't see, there are privacy issues because you can tell every time it's around 6 o'clock is when you do this activity. So they can gain insight into your movements. But if you can do all of that inference on the smart object, on the microcontroller, then there's no latency. The latency is reduced. Your costs are reduced. You're not paying for the network traffic. There's no security or privacy issues because it's local. Okay. Right. But it is challenging to do it on a microcontroller. And that's what we're interested in doing.
Amazing. So if your work is successful, which it already is to a significant degree, you are taking this significantly hard task from these services that were being provided on some cloud system, and you are now doing that particular activity, the inference, which is the decisions of the system, the AI system, but you're now doing it on a very tiny computer.
That's correct.
Yeah. Amazing. So one of the things that really caught my attention, and this is one of my last questions when I read your book, there was a very interesting case where you made the case that having like these smarter than smart systems, which actually are systems which have a machine learning model on them, could lead to possibilities like being able to track how careful a person drives, and then they could get a better premium in terms of like their vehicle insurance. Speak about that a bit.
So currently, insurance premiums tend to be the same for two people at a company. Of course, there are some companies that dedicate to female drivers. They have usually slightly lower premiums because they drive better. They are more careful when they drive. But if the two of us go to the same company, most likely we should pay the same amount, maybe just varied by size of vehicle. But we don't drive the same way. Some people drive more carefully than others. Some people take off very quickly and stop very suddenly. And by learning how people drive, you can begin to determine what makes a person a safe driver or a less careful driver. Now, if somebody doesn't drive so carefully, they are far more likely to hit something or someone. Therefore, they have to have a higher premium. Versus someone who drives very gently, they never really hit anyone, but you can tell from how they drive. So this can bring about a differentiation in how premiums are charged. So if I am a careful driver, my microcontroller learns that I am a careful driver. The insurance company, using IoT, remotely can tell this person drives reasonably well and should be charged less, right? Versus another one who drives aggressively and should be charged more. So there are lots of applications for embedded machine learning.
Amazing. I am excited. This is really one of the episodes that I am really excited because of all the possible use cases that have just come from this conversation. Sometimes when you hear these terms, especially if it is a discussion amongst the experts, it usually flies over your head and it's very hard to kind of figure out what they're talking about. But now getting to see how that could be applied in all these different circumstances really makes me interested and excited about this new field and this new opportunity area for smart systems for good. Dr. Nathan Amanquah, thank you so much once again for joining us on this podcast and sharing a lot of this very exciting information about the field of smart systems for good. And to our listeners, I am telling you to be on the lookout of Dr. Amanquah's book coming on Amazon very soon. Dr. Nathan Amanquah, it was a pleasure to have you with me today.
Thank you.